Hello everyone. Today we are looking into the fourth video of torsion. In this video, we will mainly be looking into the numerical problems related to torsion. Before moving into the numerical problems, let us take a look at the equations. One important equation that we may deal in this subject, in this section is we all know that power is force into velocity. That is in linear terms. When we take it into a rotation terms, rotary terms of power, we can write the equation, equivalent equation as torque into angular velocity. So power is nothing but torque into angular velocity. And torque, when we take it as T, capital T, and angular velocity is when it is 2 pi n by 60, where n is in RPM, n is the rotations per minute. Then we can write, combining these two t and 2 pi n by 60, we can write P power is equal to 2 pi nt by 60. Now this is an important equation in torsion. Why? Because in, in torsion, we already know that twisting moment is an important factor. The load is applied as a twisting moment. But in most numerical problems, the twisting moment is not given directly as T. We will be given the power value and the RPM value. With the power value and RPM value, we will have to find out the value of torque. So it is given, the twisting moment is given indirectly. The other equations we have already seen, and just refreshing the memory, tau max, the maximum torque, sorry, the maximum stress developed. Tau represents the shear stress. The maximum shear stress, we have already established that the maximum shear stress occurs at the circumference or the extremity of radius, the outer radius of the shaft or cylinder. The equation is given by tau max is 16t by pi d cube. We had derived this in the last video, 16t by pi d cube for a solid shaft, and it will be 16t by pi d do cube, that is outside diameter. Do is outside diameter, do cube into 1 minus k raised to 4. This equation is for a hollow shaft where k is the ratio of inner diameter to outer diameter. You must please note that this is do cube here, but it is k raised to 4 here. Now the other equation, the other combination was T by J equal to G theta by L. And I can write it as T by theta, that is load by deformation will give you Gj by L. This is nothing but stiffness. Load by deformation, always in every type of loading, the load by deformation is nothing but stiffness, equivalent to spring stiffness. Here it is called torsional stiffness. And in this, the term G into J is nothing but torsional rigidity. The other combination was tau max by R is equal to G theta by L. The uh, torsion equation, we had three terms. The different combination of any two of them can give us a platform to do our numerical problems. So this is the third combination, that is tau max by R is equal to G theta by L. And when we are dealing with this equation, this term, we must note that tau max happens at R, but it can also be written as tau by R. That is, at any radial distance small r, a shear stress tau will be developed. It will not be tau max. Tau max will be developed only at the radius, at the outer radius of the cylinder or shaft. But anywhere inside the material, any point inside the material, like if this is the shaft, any point inside the material. So the stress developed at this point will be proportional, or it will be dependent on the radial distance r here, the radial distance r. So this equation can also be written like this. Tau max only happen at points at the periphery, at the periphery. With that, we can move on to some numerical problems. So the first problem, a solid steel shaft transmits 100 kilowatt at 150 RPM. Here, the power transmission is given, the power transmitted is given, and also the RPM is given. Determine the suitable diameter of the shaft if the maximum torque transmitted exceeds the mean by 20% in each revolution. So we are asked to find the diameter of the shaft. The question here is to, our objective in this question is to find the diameter. The shear stress is not to exceed 60 megapascals. That is the limit we are given. The shear stress, the maximum shear stress the material can take is 60 megapascals. Also find the maximum angle of twist in a length of 4 meters of the shaft. So we are also asked to find the angle of twist. So what are the things given in the question? Power 100 kilowatts, revolution speed is 150 RPM. And another important fact given in the question is the maximum torque transmitted exceeds the mean by 20%. So when we calculate torque from these values, that is when we use the equation said in the previous page, we are getting the mean value of torque. But as you might have already studied in case of an engine and all, the torque level is not always a constant. The torque can vary from time to time. Even in a single revolution, at one point the torque will be minimum and another point the torque will be maximum. So we will always have to design the shaft for maximum torque. Here they are saying that the maximum torque transmitted is more than the mean torque by 20%. That is, in mathematical terms, you can write it in this manner, that T max is equal to T mean plus 20 by 100 of T mean. Then tau max 60 megapascals pascals is given, G is 80 gigapascals. We are asked to find diameter and theta. As the second part, we are asked to find the theta for 4 meters length. So initially we use the equation that was introduced in the beginning of the video. By substitution, we are substituting power in kilowatts and RPM as such. Since power is substituted in kilowatts, the answer will also be doing the calculating. The answer we will be getting will be in kilonewton meter. The kilo is due to the kilowatts here. Since we substituted in kilowatts, here we get in kilonewton meter. So that is the T mean. Now, next we will have to find the T max. T max is given, we have already established that equation. T max is T mean plus 20 by 100 of T mean. So T max is, from this equation, T max is 7.6392 kilonewton meters. So it is for the T max, maximum twisting moment, that we are going to design the shaft. Now we are asked to find the diameter. For the sake of easy understanding, I will be explaining the equations from the basics. We already know that this equation, tau max is equal to 16 T by pi d cube. This was derived in the last video. but I have written here from the basics. This equation, when I rearrange this equation, since I have to find the diameter here, in this question, the only unknown is diameter. Tau max is given, the maximum possible value of tau is given, t for which the design is to be done, we have already found out in the previous step. All others are constants. The only unknown is d here. So I can rearrange the equation to be this one, d is equal to 16t by pi into tau max raised to 1 by 3. And doing the calculation, we will get d is equal to 86.55 millimeters. You can see the calculation here and see that how the units are balanced. Since the twisting moment T is given, we have substituted in kilonewton meter, and the tau max 60, it was given as 60 megapascals. Megapascals is nothing but Newton per millimeter square. So here one term is in kilonewton and meters, the other term is in Newton and millimeter square. It is always better to convert everything to newtons and millimeters. So I'll convert the numerator to Newton and millimeter. So kilonewton is nothing but 10 raised to 3 Newton, and meter is nothing but 10 raised to 3 millimeters. So those three, 10 raised to 3 Newton and 10 raised to 3 millimeter, I'll combine it and write as 10 raised to 6 Newton millimeter by Newton millimeter square, Newton per millimeter square. So Newton and Newton will get cancelled. Millimeter cube will be here. The 1 by 3 raised to 1 by 3, when we are accommodating that power, it will finally give us 10 square millimeter. From this value, from this whatever is given in the bracket, we will get 0.8655, and when we combine this, we'll get 86.55 millimeters. Now the second part of the question. The second part of the question, we are asked to find theta. We are asked to find theta. Now I have taken tau max by r here. I could have also taken t by j, because we now know the t and j. J can be calculated because d is here. We know d. So j can be calculated. But then the calculation is going to be a bit tough. If I take this term, then the calculation is going to be a bit tough. So I will stick on to this part of the equation, this combination I will take. Tau max by r equal to g theta by n. So any combination you can try that. The other combination also you can try. Now our objective here is to find the theta. Now rearranging this equation, theta is tau max into L by g into r. We substitute the values of tau max as 60 given in the question, and length is given as 4 meters, and g is 80 gigapascals. 80 gigapascals. Gigapascals is nothing but 10 raised to 3 megapascals, that is 10 raised to 3 Newton per millimeter square. That is what is written here, 10 raised to 3 Newton per millimeter square. Plus r is nothing but the diameter by 2. Diameter we have just found out here, that by 2. So again, the equations are balanced here. The tau max Newton per millimeter square is there. Here 80 gigapascals I have written as 10 raised to 3 megapascal, that is 10 raised to 3 Newton per millimeter square. This Newton per millimeter square and this one gets cancelled. Now in the numerator we have meters, and the denominator we have 10 raised to 3 millimeters. Meter is nothing but 10 raised to 3 millimeters. So numerator and denominator cancelled out, gets cancelled out. So we will get a unit less term, but it is nothing but a radians. It is radians in SI units. It may show us unitless, but it is actually a radians. Theta we are getting in radians. So when we calculate, we'll be getting 0.06932 radians, and that when converted to degrees, it will be when you multiply with 180 by pi, you will get the answer as 3.97 degrees. So you must always remember that theta in this calculation we will be obtaining it as radians, except with sine and cos, uh, those trigonometric relation. When we are using theta in calculations, degrees, angles in calculations, we will get it in radians only. So that is the first question. Now we'll move on to the second question. A hollow steel shaft transmits 200 kilowatts of power at 150 rpm. Again, the power and rpm are given. Here it is hollow steel shaft. The shaft is hollow. The equation now changes. The first one was solid shaft. The total angle of twist in a length of 5 meters of the shaft is 3 degrees. Now they have given the angle of twist. It is given as 3 degrees, that is in a length of 5 meters. Now we are asked to find the inner and outer diameter of the shaft if the shear stress, permissible shear stress, that is the maximum shear stress possible, is 60 megapascals. G is again given as 80 gigapascals. So in this case, initially I have in the beginning itself, I'll be converting all the units to basic units, that is to newtons or Newton equivalents and millimeters. So power, I will be taking it as 200 into 10 raised to 3 watts. I will remove the kilo here. Speed in RPM itself. Then theta is given in degrees. Remember, to use it in calculations, we will have to convert it into radians. And the length is given as 5 meters. We will be using it as 5000 millimeters. Tau max is 60 megapascals. Megapascals is Newton per millimeter square. So already given in our required terms. And G is 80 GPa, that is 80 into 10 raised to 3 Newton per millimeter square. And we are asked to find outside diameter and inside diameter. So outside diameter, first I will be moving to find one of the combinations I will use here. Now, in the previous question we started by finding T. Now I could have started with that here also. T by J equal to T by J equal to, here the limiting condition is given as tau max. So I could have started with this combination, but here I don't know the outside diameter and inside diameter. So the calculation or the two unknowns, if I take it all together at the beginning itself, the calculations can be a bit difficult. So I'll be minimizing the initial unknowns. I don't want to take the two unknowns together. Now, if I take this combination, there is only one unknown. The inside diameter do not play a part in this combination. So that's why I have started with this one. If you want, if you feel comfortable, you may start with this combination. That is, you can take T by J initially. T by J is equal to G theta by L, or T by J is equal to tau by R you can take. But then you will have to connect the equations. With one equation you can solve only one of the unknowns. This J contains both outside and inside diameter, both of which we don't know at this stage. That's why I skipped this part of the equation. I am not getting into this at present. So tau max by R0 equal to G theta by L. This combination I am taking, and I'm converting the theta to radians by multiplying it with pi by 180. Then the direct substitution, the equation, the units were all initially put in such a way that it all gets balanced. There is no confusion with that. Then just direct substitution will get the value of RO, that is the outside radius, which multiplied by 2 will give you the outside diameter, that is 143.24 millimeters. Now we have to find the inside diameter. Now we will use T by J. because now there is only one unknown here. So this equation, again, we are utilizing this equation, P is equal to 2 pi nt by 60. From this, we will be getting T as, we'll be getting the T value in Newton meters, 12732.4 Newton meters. Then we'll be converting, just because this is in meters, I don't want any units to be in meters. I want all length units to be in millimeters. So I will be multiplying into meters is nothing but 10 raised to 3 millimeters. So into 10 raised to 3 Newton millimeter. So now I can utilize this equation, T by J equal to tau max by Rho. Here the only unknown is J. T is known here, we just found out. Tau max is given in the question. Rho was found out in the initial part of the solution. Now just substituting the values, we'll get the value of J as this. Rearranging and substitution will give you the value of J as this one. Now J, we know that it is nothing but pi do raised to 4 minus di raised to 4 by 32. So here the only unknown is di, the inside diameter. Inside diameter is the only unknown. So rearranging everything, every other values we know. We know the value of do now. So now we can rearranging the equation and so solving it for finding out di, we get the value of di as 127.73 millimeters. So outside diameter was 143.24, inside diameter is 127.73 millimeters. So that's the solution for the second question. Now let us move on to the third question. On this question, we are asked to compare the weights of equal lengths of a solid and a hollow shaft to transmit a given torque for the same maximum stress if the inside diameter of the shaft is 3/4 of the outside. Now, this question may seem to be a bit complicated because you are asked to compare the weights. So let us put it in a simple way. So weight, we will be taking it as W. Now you are asked to compare the weights of solid and hollow shaft. So that is, you are asked to find the ratio. By comparison, you can understand that as you are asked to find what fraction of weight of solid is hollow shaft. So you are asked to find the ratio of weight of solid shaft to weight of hollow shaft. Now, in the question it is given that length L is same, torque applied P is same, and the tau max, it is the same material. So the maximum permissible stress is also same. All are same. And another important factor given in the question is di by do, the ratio of inner diameter to outer diameter is, that is K. In our basic equation, we have established it as K is nothing but 3/4. Now, to break down this further, to simplify it further, weight by weight is nothing but density into volume. Now, here the material we are assuming to be same because it is not mentioned that the materials are different. So we can assume that the materials are same. So the densities are equal. So the weight ratio becomes volume ratio. Now, volume of a cylinder or a shaft is nothing but area into length. Now, it is specifically told in the question that the lengths are same. So the length also get cancelled out. Now, the weight ratio becomes area ratio. So in effect, in this question, we are asked to find the ratio of area of solid to area of hollow, or reverse. You may take it as reverse also, area of hollow by area of solid shaft. So that is what we have to find out. So this is our objective, to find this ratio. This ratio. This is our objective. Now, since we have established that, now let us move into the solution. That is, the equality of length is already utilized in our previous steps. Now the tau max and T are same. That is given in the question. So to utilize that equality, I will be taking this equation. That is tau max is equal. Same for both the shafts. So tau max, we already know the equation of 16t by pi d cube, 16t by, and this is for a hollow shaft, 16t by pi do cube by 1 minus k raised to 4, where D is for solid shaft. This is for solid shaft. This is for solid shaft. This is for hollow shaft. Now, since T is also same, it is given that the torque or twisting moment is also same. Here, the only difference is D and DO cube, D and DO. Okay, so I can simplify this equation as D cube is equal to DO cube into 1 minus K raised to 4. The K value is already given in the question. It is given as 3 by 4. So I can substitute that and I can relate the outside diameter of hollow shaft and the diameter of solid shaft. So there is a relation between the diameter of solid shaft and outside diameter of hollow shaft. With that relation in mind, we can move on to the initial. That is, we are asked to find this value. Let us look into that. So what is actually AS by AH? You can substitute the expression for area, pi d square by 4. For a solid shaft, it is pi d square by 4. For a hollow shaft, it is pi do square by di square by 4. Now, pi by 4, they are same. So I can again simplify this equation as d square by, I can, from this bracket, I can take the outside diameter, do outside, do square outside, then I will get it as 1 minus di square by do square. Di by do is nothing but k, so I can write it as k square, 1 minus k square. K value, again I know that is 0.75 or 3 by 4. So 3 by 0.75 square, 1 minus 0.75 square will give you 0.4375. So this is the required, fraction. Now we have already established D equal to DO into 0.881. So that we can substitute here. Instead of D, I can substitute 0.881 DO. So the whole square. Then solving it, we can get the value as solid shaft area to hollow shaft area will be equal to 1.77. That is, the weight ratio of solid to hollow is 1.77. You can take the reciprocal, that is, hollow to solid shaft is 0.56. One important thing to note from this problem is, for resisting the same torque with same maximum permissible shear stress, the hollow shaft is taking much less weight or consuming much less material compared to solid shaft. So by design parameters, so by any indexes of design, a hollow shaft is way better than a solid shaft, because it, for resisting the same load, it is taking lesser amount of material. So hollow shaft may be better. In many cases, it will be hollow shaft is better than solid shaft because it is consuming less material. The weight is less, and that indicates that the amount of material that goes into it is also less. Now, this type of problem, you may be asked, here it was to compare the weights. Sometimes in another problems, you may be asked to find the resistance to twisting moment. Then that is nothing but T. You are asked to find the TS by, you are asked to find the TS by TH, similar to here. Because in our derivation, I had already told you that the T that we find in the torsion equation, it is actually the resisting torque. It is the resistance offered by the material. It is not the applied torque. But in most of the cases, this will be equal. The resisting torque and applied torque will be equal. So we can take it interchangeably. But if they ask the resistance to twisting moment, compare the resistance of one shaft over the other shaft, resistance offered by uh, one shaft compared with resistance offered by another shaft, the resistance to twisting moment. Then they are actually asking you to find the ratio of twisting moments only. So that's it. Thank you.